Hello everyone, this is Yu from the National University of Defense Technology. Today I'm happy to introduce my paper CD-SGD, Distributed Stochastic Gradient Descent with Compression and Delay Compensation. Yu is the first order. Dong is my instructor and the corresponding author of this paper. Distributed training has become an effective method for deep learning model training. The enormous training dataset is divided among multiple nodes for training tasks. As a result, these nodes must communicate these calculated parameters with each other before updating global parameters. The communication cost limits the scalability of system and reduces the efficiency of training seriously. For example, this page shows the process of using 4 workers for distributed training. Training can be divided into calculation phase and communication phase. In the calculation phase, every worker completes their assigned task and calculates new parameters. Since the training samples obtained by each worker are different, these parameters are localized, so the workers need to exchange parameters with each other and send the parameter to the server for processing. Then the server processes the required parameters and sends them back to the workers. From this animation, we can also find that the process of parameter communication is relatively time-consuming. There are two mainstream weight updating algorithms, synchronous and asynchronous, in the distributed training process. The synchronous updating algorithm model has high accuracy, but its training speed is slow. The asynchronous updating algorithm breaks the synchronous fence mechanism and has fast training speed, but the weight delay leads to the decline of the accuracy of the model. The key to optimize the synchronous update algorithm is to optimize the communication overhead. Well, the key to optimize the asynchronous update algorithm is to ensure the accuracy of the module. Our work focused on optimizing the synchronous update module. The optimization of synchronous updating training mode can be divided into system-level methods and algorithm-level methods. In this page, we introduce two optimization strategies: establishing local update mechanism and compressing gradient. The former is system-level method, and the latter is algorithm-level method. As previously introduced in SSGD, workers must communicate to synchronize parameters. Each worker cannot start the next round of calculations until communication is completed and new parameters for calculation are obtained. But if we introduce a local update mechanism to provide the required parameter for the next calculation, the next calculation can be performed at the same time as the current communication to cover up the communication overhead. However, because the input parameters required for the local update come from the previous global update, when the communication overhead is too large, the calculation cannot completely cover all the overhead. Many researchers use low precision gradient data to replace high precision gradient data for communication, or only transmit gradient data exceeding the threshold to reduce the communication burden, which can reduce the first communication overhead. However, there are two problems to be noted in this strategy. Firstly, the use of incomplete data will lead to the decline of accuracy. And secondly, it will introduce additional computational overhead during data conversion and data filtering. The challenges mentioned, we propose CD-SGD. It explores gradient quantization and delayed for gradient compensation to accelerate the distributed training while preserving convergence accuracy. As shown in the figure, after each calculation, the worker will immediately start to compress the generated parameters and start local update. The two operations are carried out in parallel. The compressed parameters are then passed out for communication, but net calculation doesn't need to wait for the communication delayed by the compress operation. Besides, we designed a periodic accuracy correction named the key step correction to solve accuracy degradation caused by gradient compression. The design logic of key step correction is use for gradient communication periodically to help global widths correct in time in the right direction. In order to verify whether our implementation is effective, we use the preferred MXNet to record the execution sequence and time cost of each operation in a certain period of time during the ResNet 20 model training process. After that, we use the trace viewer in the Chrome to display the obtained data. The figures in this page record the working data of beta-SGD and CD-SGD between 100 and 200 milliseconds. For beta-SGD, FBB has to wait for the end of communication in the previous iteration to start. However, this phenomenon doesn't appear in CD-SGD. For example, the fourth FPBP starts before the third communication ends. Therefore, the start time of next iteration has nothing to do with the current communication. The quantization overhead can be seen as being hidden. Perhaps the reader will have the idea that the quantization overhead is carried by the communication cost. In fact, the quantization and communication are carried out on a layer-by-layer basis, and each layer of quantization cannot start until its corresponding BP calculates the gradient. In this case, quantization cannot be parallel to communication. We set three groups of experiments: train the 95 model with minutes dataset, train exception with cipher 10 dataset, train ResNet 50 with ImageNet dataset. No matter train with 2 workers or 4 workers or 8 workers, the accuracy of beta-SGD performs worse than that of the other approaches, obviously. However, CD-SGD solves the problem of beta-SGD, and its performance is very close to SGD when training the 95 and ResNet 50, and even higher when training exception. These three experiments not only reflect the adaptability of CD-SGD to different models and datasets, we also test the effects of different warm-up epochs and number of workers on CD-SGD. When training ResNet 50 with 4 nodes, CD-SGD takes 5 epochs to warm up. While training exception, CD-SGD uses more than 20 epochs to warm up. More warm-up epochs are helpful to improve the accuracy of CD-SGD, but only use 5 epochs to warm up is okay. To analyze the influence of K on accuracy, we train ResNet 20 on cipher 10 dataset with 2 and 4 workers. We can get the following observations. Firstly, CD-SGD always achieves the best accuracy when K is 2. The accuracy decreases as K increases, and it is obvious when more nodes are used. When K becomes infinite, CD-SGD can be regarded as an algorithm without K-step correction. In this case, its accuracy is close to that of beta-SGD. The table regards the average epoch wall clock time and communication time in one epoch of various algorithms, in which TE is the average epoch time, TC is the communication time. In this table, K has no effect on training speed, because the communication cost of beta-SGD is close to that of SGD. In addition, since the measurement tool will affect the training performance, we only select one epoch to record the communication time, which will have some impact on the results. In order to observe the speed of each algorithm, We tested them on K80 and V100 GPU separately, and the speed of SSGD is the baseline. When training Resonant 50 on K80, CD-SGD gets the same training speed as SSGD. We attribute this phenomenon to the limited computing power of K80, which leads to the bottleneck of computation. In the speed test experiment, the key step of CD-SGD is 5. The V100 GPU has more computing power, which can complete the computation task in less time. As the bit size becomes bigger, the accuracy effect of CD-SGD is weaker. The reason for this phenomenon is the larger bit size training brings greater computational pressure. In this case, the computation becomes the bottleneck of training. The performance improvement range of CD-SGD to SSGD and bit-SGD is 0 to 89% and 3% to 45% respectively. Our conclusions are shown as following. Firstly, the distributed training communication optimization is necessary. Besides, there are 3 challenges in combining compression methods with system-level methods. There are additional compression overhead, accuracy decline, and sufficient benefits is in need. Thirdly, the local update mechanism can cover the additional computational overhead of compression. Finally, key-step correction method can solve the accuracy reduction problem of the compression method. My presentation is over. Thank you.